Hello everybody. Today we are going to start the last chapter in two-dimensional geometry, that is called the polar equations. Polar equations, this is actually an equation involving the polar coordinates of particular curve. And what are polar coordinates? We know that in order to represent the position of a point, generally we have the concept of coordinates. We introduced the concept of coordinates, and we discussed about the Cartesian coordinates. Coordinates is actually a reference frame, and in order to study the geometric aspects, we always require a reference frame. So far we have discussed about only Cartesian coordinates, and similar to Cartesian coordinates, we have different other reference frames as well. And one such reference frame or the coordinate system is called the polar coordinates, the polar coordinate system. Over here, in polar coordinates, we always require a fixed straight line and a fixed point. These are the two requirements with respect to which the position of the point is measured. This fixed point, generally it is denoted by O. This is called the pole, and this pole is different from the concept of pole and polar. Okay, this is called pole. This fixed point O is called pole, and this fixed straight line through this fixed point, this kind of fixed straight line OX through this fixed straight line, this is called polar axis or the initial axis. Okay, polar axis or the initial axis. This kind of straight lines are called polar axis or the initial axis. Okay, in some books like this, in this book they have taken this fixed point O as the origin, but this concept of origin is not related with the concept of polar coordinates. The concept of origin is actually related with the concept of Cartesian coordinates. Okay, that's why in future we shall study this fixed point O as the pole, not the origin. All right. So pole and origin may coincide, may not coincide. In fact, in the subsequent lectures, we shall see that the pole in this polar coordinate and the origin in Cartesian coordinate, these two are different points for representation of the equation in polar and Cartesian coordinates. So these two would be two different points, and that's why origin should not be, this word origin should not be used. That's why I have crossed this word origin. Okay, be very careful about it. Some mistakes are always there in most of these books. No book is foolproof. All right, and now what is what are the polar coordinates with respect to these two fixed points, the pole and this initial axis? We consider a circle like this kind of circle, this kind of circle with center O, and passing through a particular any arbitrary point P. Suppose we want to find out the polar coordinates of this point P. Then how to find out the polar coordinates? We generally try to draw a circle, and you can also think this one in this fashion. If you don't want to draw a circle, in that case you can think like this, that you just draw the straight line joining this point P and the point O, and this distance, that is actually the radius of a circle with center O. That's why we considered this kind of circle. Radius of a circle with center O. In that case, this distance is called the radius vector of the point P. Over here, this is the idea of radius vector. Radius vector of the point P. Okay, the radius vector of the point P, and the angle made by this straight line OP, and the measurement of the angle starts from this initial axis in anti-clockwise direction. Hmm. This angle is denoted by theta, and it is called the vectorial angle. Remember, this angle is always measured in anti-clockwise direction. The anti-clockwise direction is taken as the positive direction in this kind of measurement. All right, the clockwise direction is taken as the negative direction, and anti-clockwise direction is taken as the positive direction. Okay, so this kind of angle is called the vectorial angle. This is the vectorial angle theta, and it is measured in anti-clockwise direction. Okay, so we can say that at least in the polar coordinates we don't need this idea of circle, so we can delete this idea of circle. However, the term radius vector comes from the idea of the circle, that this is actually the radius of a circle with center situated at this fixed point O, and the radius is equal to the distance OP. That's why I introduced this circle over here. All right. Now, um, in this polar coordinates, hmm, there are some mistakes in this book. You see, suppose this point P has a certain vectorial angle, suppose equal to theta. Hmm. Suppose this angle is equal to theta. Then what would be the vectorial angle of this point P2? You see, vectorial angle is always represented in anti-clockwise direction. This angle would be the vectorial angle of the point P2. So the vectorial angle of this point P2 should be is equal to theta plus 180 degree or theta plus pi. Okay, if it is measured in radians. So theta plus pi radian would be the vectorial angle of P2. Do not ever consider this vectorial angle is equal to in this much. In some books it is written in this way, but that is also a concept, because this is measured in anti-clockwise direction, so this can be again considered as equal to a vectorial angle of this angle would be negative of Hmm. Negative of pi minus theta. Got it? That is also permissible. But the major mistake that in some books you will find, this major mistake is that you see this radius vector is a length, measure of a length of the distance OP. Therefore, this radius vector is never negative at all, and that is the major mistake that some books in some books you will find this mistake, that the vectorial angle of PT is taken as the negative quantity. Suppose this is equal to R and this angle is equal to theta. In that case, the position vector, the polar coordinates of the point P1 becomes is equal to R and theta. Okay, fine. Now, what is the position? What is the polar coordinates of this point P2? In some books, you will find that this distance is equal to minus r comma theta, because r is measured in negative direction. But remember, by definition, the distance r is always a positive quantity. It can be equal to 0. If one point coincides with the other point, then that distance may be equal to 0, but it is never negative. Therefore, this idea of coordinate is a wrong idea. Okay, then what would be the correct coordinates of the point P? You see, if these two distances, if this distance and this distance, if these two distances are same, suppose this distance is also is equal to r. Okay, in that case, the radius vector would be is equal to r. Just the difference would be in the vectorial angle. If this angle is theta, then this angle would be is equal to pi plus theta. Therefore, the vectorial angle should be is equal to theta plus pi radian. Got it? That should be the correct representation of the point P, the polar coordinate wise representation of the point P. And you will find this kind of mistakes over here. You see, minus 2 comma 30 degree angle, this kind of minus 2 radius vector can never be equal to minus 2. So minus 2 comma minus 120 degree, this is also a wrong representation. Got it? So be very careful about this kind of minus of r. These are the wrong representation. So the radius vector can never be negative quantity. Now suppose we want to find out the relation in between the polar and the Cartesian coordinates of any particular point P. Hmm. In that case, if this point O, that is the pole in case of polar coordinates, and if the same point is considered as the origin in case of Cartesian coordinates, then only we have this standard formula that is equal to, that is the formula x is equal to r cos theta, y is equal to r sin theta. So that tan theta is equal to y by x. Okay, and r is equal to root over of x square plus y square, positive square root. Mind it, they did not ever consider negative square root. They always consider positive square root. We always consider positive square root because r is a length. It can never be negative. Hmm? Now, there are certain problems with this kind of transformation. What are these problems? You see, if we consider x is equal to r cos theta and y is equal to r sin theta. So, you see, whenever r and theta, these two quantities are known, then by this kind of formula number 1 and formula number 2, we can find out the expressions of x and y. Fine. We don't have any problem in this case. And over here as well, you see whenever x and y, these two Cartesian coordinates are known quantities, then we can find out the value of this r by the formula root over of x square plus y square, and theta can be tan inverse of y by x. Isn't it? Theta would be is equal to tan inverse of y by x. But over here in this formula, we have a problem. What is the problem? The problem is that if by chance x becomes is equal to 0, then even then it is okay. If by chance x is equal to 0, some finite quantity divided by 0, that is equal to infinity, so that theta would be is equal to pi by 2. Okay, but the question is that whether it is plus infinity or minus infinity, it depends upon the sign of y. If y is positive, then we call it plus infinity. If y is negative, then we have minus infinity, and accordingly theta will have the value plus pi or minus pi. So this is not a problem. The problem is that if along with x is equal to 0, further y becomes is equal to 0. If along with x is equal to 0, further y becomes is equal to 0, then you see we have some quantity like 0 by 0. And what is the value of 0 by 0? That is not defined in any real analysis. The mathematicians actually, what we do is that whenever we face any problem, we just keep that unsolved and we try to move forward, because whenever it is a problem to which we do not have any answer, any proper answer at all, then we keep that unsolved, and we try to develop the mathematics in such a way that we can move forward. And this is the position where if x and y both are equal to 0, then we have 0 by 0, this kind of situation, and 0 by 0 is not defined at all. Although y by 0, you see y by 0, this is also not defined at all, but this y by 0 can be considered in this way, that y divided by x, where x is tending to 0. Hmm. So we can say in the numerator, if this is a finite number and this is very small and small number tending to 0, then of course this ratio would tend to plus or minus infinity as according as this numerator value of y is positive or negative. So it would tend to plus or minus infinity according as this numerator value of y, this is positive or negative. So in this way, when only x is equal to 0, we can have an interpretation. But if along with x is equal to 0, y is also is equal to 0, then we do not have any definition, any interpretation of this 0 by 0. And if we want to apply this kind of idea of limit, say y tending to 0 and x is also tending to 0, in such cases we find that value of this expression is sometimes 1, sometimes it is 2, sometimes it is infinity, sometimes it may be equal to 0. And that is related with the idea of L'Hospital's rule or L'Hopital's rule. Hmm. However, we do not have any definite answer that what would be the value of this type of quantities whenever y and x both are tending to 0. So this is an undefined object when y by x is when y and x both are equal to 0, then 0 by 0, this is actually an undefined object and we call it indeterminate form. Indeterminate. Okay, indeterminate forms. Indeterminate indeterminate N-A-T-E. Indeterminate forms. And this kind of indeterminate forms, indeterminate means which is cannot be exactly determined. We can determine their value, but depending upon the situation, the value of this may be different for different situations. That's why we call it indeterminate forms. Hmm. And in such cases, this kind of transformation, tan theta is equal to y by x, is actually not valid at all. Then what should we do whenever x and y both are equal to 0? X and y both are equal to 0 means we are talking about the origin, the point 0 comma 0. What would be the polar coordinates of the point 0 comma 0? You see, we do not have any problem with this formula of radius vector r. Okay, therefore we can say that the polar coordinate, the first polar coordinate r, that r would be is equal to 0. Okay, fine. And what would be the value of theta, the second coordinate? And that is the special case. We assume that this value becomes is equal to theta. We say this value becomes is equal to 0. We say that in case of origin, theta should also be equal to 0. So what we can say? We can say that this formula is true for in this way that whenever x is not equal to 0, tan theta should be is equal to y by x. And whenever x becomes is equal to 0, this tan theta would be is equal to 0, so that theta becomes is equal to 0. Got it? Therefore, we should write theta in this fashion. You see, theta is equal to tan inverse of y by x when x is not equal to 0. And this should be is equal to 0 when x is equal to 0. Got it? Therefore, this should be the proper definition of theta, and in this way, we also cover this confusing position so that 0, 0, this 0, 0 becomes the polar coordinate of the origin as well. Now, it may so happen that the Cartesian, this origin and the pole of the polar coordinates, these two may be different. You see, this may be the, not in this way, rather we can draw in this way. You see, this may be um, the x and y coordinates, and then this would be the position of the origin, and the pole and the radius vector can be considered in this way. Therefore, we can say that this is the pole. This point would becomes the pole, hmm, and this is the radius vector r. This would be the angle theta. Hmm. And this is the origin O. This is the x-axis and this is the y-axis. Hmm. Therefore, in this case, the pole and the origin may be different. Hmm. And of course, in that case, x is equal to r cos theta and y is equal to r sin theta. This kind of formula do not hold at all. We would have different kind of formula for this, and you already know about the transformation of coordinates in two dimensions, so you please think over it. What could be the transformation formula from xy coordinate system to r theta coordinate system? Okay, and on that transformation formula we should have the kind of modification as I told you over here. We should also introduce the kind of modification in order to find out the value of theta. So I am keeping this kind of result, this kind of transformation formula for you as a homework. You please think over it. What I think that the knowledge you have so far from your class 11 12 level geometry and the form the geometry of Cartesian coordinates discussed so far, hopefully you would be able to find out the transformation formula. We need the transformation formula A for x and the transformation formula for y in terms of r and theta in this kind of situation. Okay, so I'm keeping this result as a homework for you. Now, let me move to the traditional results that we generally discuss. You see, if you recall your geometry in 11 and 12, you would find that firstly the idea of coordinate was introduced in Cartesian form, and then the formula for distance for computation, the computation of distance in between two points, say the point P and the point Q. The point P may have the coordinates x1, y1. The point Q may have the coordinates x2, y2. Then you got the formula to find out the distance in between P and Q. That was the formula for distance, and that was the idea in case of Cartesian coordinates. Now we are introducing the same kind of idea or same kind of formula in case of polar coordinates over here. Hmm? Suppose this point P has the polar coordinates r1 and theta 1. Sometimes we generally call P has the vectorial angle theta 1. Okay, we mean that the corresponding polar coordinate is equal to r1. Okay, so this kind of notation is also available in different books. Be careful about it. Now, suppose the polar coordinate of the point Q become r2 and theta 2. Hmm. Then the question is that what is the formula for evaluating this distance d in between the points P and Q? Hmm. You see, we can consider this kind of triangle, the triangle O, Q, and P. And in the triangle, we have a formula that C square is equal to A square plus B square, minus twice AB into cos of C. What is C? C is actually in a triangle. This angle C is actually the opposite angle to the edge small c. Hmm. To the edge small c. This is the edge A. This is the edge B. Got it? Hmm. So A and B, this is the edge small a and this is the edge small b. So in this way, we can find out the square of this distance C. So over here, in place of C, you find that we have the distance D. In place of this distance A, we have this distance R2, and in place of this distance B, we have this distance R1. So we can apply this formula for this triangle OP and Q, and by that formula you will see that d square would come in place of c square. Got it? This d square would be is equal to r1 square plus r2 square minus twice r1 r2 cos of what would be the angle? This would be the angle, just the angle opposite to this edge. You see, we are interested to find out the distance, this d. Therefore, we should consider the angle opposite to this edge d. So the angle should be is equal to POQ. That means this angle is actually nothing but is equal to theta 1 minus theta 2. Got it? So this would be the corresponding formula over here. You look at this formula. This is the formula r1 square plus r2 square minus twice r1 r2 cos of theta 1 minus theta 2. Therefore, we got the square of the distance, that is PQ square. Therefore, PQ should be is equal to the positive square root of the expression on the right hand side. Here, so in this way, we find out the distance between 2 points in case of polar coordinates. Okay. Now, we got the formula for distance between 2 points in terms of polar coordinates, and in this polar coordinate, in this formula you would observe that we have cos of theta 1 minus theta 2. So even if you consider theta 2 minus theta 1, in place of theta 1 minus theta 2, if you consider theta 2 minus theta 1, you would get the same expression. Why? Because cos of theta 1 minus theta 2 and cos of theta 2 minus theta 1, both of these two quantities have same value, the numerical value of cos of theta 1 minus theta 2 and the numerical value of cos of theta 2 minus theta 1 are same. So the formula remains intact whether whatever combination you use, theta 1 minus theta 2 or theta 2 minus theta 1, it doesn't matter. All right. Now, let's try to find out the area of a triangle. Suppose we have a triangle A, B, and C, and suppose this A has the polar coordinates r1 theta 1, this point capital A. The point capital B has the polar coordinates r2 theta 2, and the point capital C has the polar coordinates r3 theta 3. And we want to find out the area formed by this triangle ABC. The area of the triangle ABC, we are interested to find out the area of this triangle. Now you see, we already have a formula for evaluation of area of a triangle. If suppose we have a triangle like this, and suppose this is the point and this is the edge A, this is the edge B, this is the edge C. Okay, and this angle is equal to the angle C. Then we have the area of the triangle. The formula is equal to half of A B sine of sine of this angle in between the adjacent edges. This A and B, these are two adjacent edges. Then we have to consider the angle in between these two related or adjacent edges. So that should be the angle sine of C. So we already have this formula, and we are going to apply this formula in the evaluation of the triangle ABC. Now, how to find out the area of the triangle? You see, let me divide this. Let me divide this segment, this screen into two portions. Mm. So this is the area. This is the triangle. Mm. Let me minimize it a bit. Okay. Now let's move on over here. You see, the area of the triangle is ABC. Hmm. So we can firstly consider the area of this total triangle, this triangle, this triangle, area of this triangle. Hmm. That is the triangle AOC. We can also consider the area of this triangle, the triangle AOB. We can consider the area of this triangle. And then from this total area, so what we got, we ultimately got, we have the area of this quadrilateral OABC. Now from this total area, we are going to subtract the area of this triangle. We are going to subtract the area of this triangle, that means the area of the triangle OBC. That's why we are individually computing the area of all these three triangles. The first triangle is the triangle OAB. So the triangle OAB or AOB, area of the triangle can be considered to be is equal to the area of the triangle can be considered to be equal to using this formula. You see, if we can consider this edge as the edge small a, we can consider this one as small b, and this angle, the angle between these two adjacent edges, we can consider this angle to be equal to capital C. Okay, therefore we can apply this formula, half of AB sine C. So half of AB means AB. A means this distance from starting from O to the point capital A. Therefore this is our distance small a. This is OA into B, that is actually OB, and sine of the angle BOA, sine of this angle BOA, that is actually the angle C over here. Okay, so in this fashion we can compute the area of the triangle OAB, and the what is the area? You see, OA means the radius vector of this point capital A. The radius vector of this point capital A, that is actually this distance OA. That's why we have this expression of R1. Then this distance OB is equal to the distance R2, and the angle, that is the actually the angle C is actually the difference of the vectorial angles of the point B and the vectorial angle of the point A. The vectorial angle of the point B was equal to theta 2. And the vectorial angle of the point capital A was equal to theta 1. Got it? So we can say that this angle BOA, that must be is equal to sine of theta 2 minus theta 1. So in this way we get the area of the triangle OAB. Now, in similar fashion, we can find out the area of the triangle OAC. You see, that should be for in case of this triangle OAC, O, A, and C. In case of this triangle, sorry. In case of this triangle OAC, you see the adjacent sides should be is equal to, over here you can consider this side is equal to small a, this length should be is equal to small b, that means OA, starting from O to this point capital A, that can be considered as equal to small b, and this angle, this angle can be considered as equal to the angle C. Therefore, OA is equal to small a over here. OC is equal to this distance B over here, and angle AOC, this angle AOC, that is actually this angle over here. And what is angle AOC? That if you look at this picture carefully, let me show from this figure. You see this angle, this angle should be is equal to, you see, theta has the C has the vectorial angle theta 3. C has the vectorial angle theta 3 and capital A has the vectorial angle theta 1. Got it? And therefore this angle should be actually the difference in between these two vectorial angles. The larger vectorial angle is theta 1 and the smaller vectorial angle is theta 3. Therefore we can write over here theta 1 minus theta 3. Got it? We can write theta 1 minus theta 3. And similarly we can find out the angle area of the triangle BOC. That would be is equal to half of R2 R3 sine of theta 3 minus theta 2 minus theta 3. Got it? Sine of theta 2 minus theta 3. And this sine of theta 2 minus theta 3 can be written as negative of half R1, R2 R3 into sine of theta 3 minus theta 2. Now we got the area of these three triangles. You please be very careful about their sign. Sometimes we get theta 3 minus theta 2 minus, sometimes theta 1 minus theta 2, etc. So you may get confused. And in order to reduce this confusion, what we generally do, you ultimately you would get this final formula that as I told you, that area of the triangle ABC, area of the triangle ABC, that means this much area. We are interested in this much area, that can be considered as equal to area of this total first triangle, then area of this second triangle minus the area of this third triangle. We are subtracting the area of this third triangle. So area of this first triangle plus this second triangle minus the area of this third triangle. And due to this minus sign, and the area is also written in terms of this minus symbol. And both of these two would together form a positive symbol. And ultimately we would get half is taken common over here, half of R3 R2 sine of theta 3 minus theta 2. Got it? Sine of theta 3 minus theta 2. And what is the advantage of this kind of representation? The advantage is, let me show you from this picture. Advantage is that if you consider 1, 2 and 3 and write them in any particular order, either in increasing order or in decreasing order, or you can write it in cyclic order. Over here I am writing this cyclic order from 1 to 3, then from 3 to 2, and then from 1, and then from 2 to 1. You can consider the opposite order as well, it doesn't matter. Just a matter of plus or minus sign would ultimately come. You see over here, the first term is R1 R2 or R2 R1, it doesn't matter. Whatever expression you write over here, it doesn't matter. We are actually interested in writing this expression of this R2 minus R1. Therefore, I am writing starting from 2 to 1, we have an arrow. Got it? R2 minus R1. In the next term, we will get R1 minus R3. Therefore, starting from 1 to this point, this index 3, R1 minus R3. Theta 1 minus theta 3, not R1 minus R3. Theta 1 minus theta 3, 1 minus 3, this kind of idea. And the third term is R3 R2, and that is about theta 3 minus theta 1. So 3, starting from 3 to theta 3 minus theta 2, not theta 1, theta 3 minus theta 2. So starting from 3 then up to the index 2. So ultimately you get a cyclic order formula, and in such cyclic order formula these all terms are positive terms. Got it? All terms are positive terms. You can write R1 R2, you can write R3 R1, it doesn't matter. You can write R2 R3, it doesn't matter. But you just always follow this kind of cyclic order, then this formula becomes correct. Otherwise some symbol positive and negative symbol would make you confused. Hmm. So that's why I have written this formula in this fashion. Just this kind of arrow would help us to write this kind of formula, and that is the formula for triangle only. Hmm. We have we can extend this formula to quadrilateral or any polygon with n number of indices. You see, you can then consider this kind of polygon with n number of indices. Then from 2 to 1, that is one result from theta 2, theta 1, then theta 3, theta 2, and finally last term would have the opposite kind of result, the theta 1, theta n. You see, you can write we can write over here, suppose 1, then 2, then 3. In this way you can continue up to n. Hmm. So what is the order over here? Theta 2 minus theta 1. So theta 2 to 1. This is one formula. Hmm. Then theta 3 minus theta 2. So from 3 to 2 you get one more arrow. In this way you can continue. So ultimately you would get some arrow in between n and 3. Okay, and in the last term you have theta 1 minus theta n. So over here you see theta 1 minus theta n, then starting from 1 to n you will get one more arrow. So in this way you will ultimately get a cyclic order in between the indices 1 to up to n. That's all about the area of a polygon or the area of a triangle. And if suppose in the area of the triangle, from this result we can compute the result under which 3 points or more than 3 points become collinear. That means all these 3 points lie on a single line. You see, if 3 points lie on a single line, in that case the area formed by these 3 points, area of the triangle formed by these 3 points, that area must be is equal to 0. If these 3 points, say one is this point capital A, another is the point capital B, and suppose there is a third point capital C. If these 3 points lie on a single straight line, then the area formed by these 3 points, area of the triangle formed by these 3 points A, B, and C, that area of the triangle must be is equal to 0. Therefore, if we put in this formula of the triangle, this is the formula of the triangle. If we put this area is equal to 0, then half would ultimately cancel out because of this 0 on the right hand side. So no half would ultimately appear, and ultimately you will get this kind of formula. This is the condition under which these 3 points A, B, and C with polar coordinates r1 theta 1, r2 theta 2, and r3 theta 3. These 3 points would be collinear. Got it? So under this condition, these 3 points become collinear. This is the condition of collinearity. Now let's move to the next idea. That would be the equation of a straight line, the polar equation of a straight line. Suppose we are interested to find out this kind of straight line, the straight line on this straight line we are drawing a perpendicular line, this kind of perpendicular line from the origin. Got it? Or the pole. We are drawing a perpendicular line from this pole O. And suppose this perpendicular distance is equal to P, and this angle is equal to the angle alpha. This angle is equal to the angle alpha. Now, how to find out the equation of a straight line? In order to find out the equation of any curve, what we generally do, we generally take any arbitrary point. We have taken capital R over here, this kind of arbitrary point on the curve. over here the curve is actually the straight line. So on this straight line we are taking any arbitrary point r. And if we can find out the any relation in between the coordinates of the point r and theta for this point capital R. The coordinates, the polar coordinates, we shall consider the polar coordinates because we are interested in the polar equation of the straight line. That's why we shall consider the polar coordinates. So one polar coordinate is equal to small r, another polar coordinate is equal to theta. And we are interested to find out a relation in between r and theta, and that would be the polar coordinate of this total straight line, because this straight line would be actually the locus of this kind of point like r, capital R. So we first assume that the polar coordinates of this point are this small r and theta. Small r and theta. And over here you see, if we join this point r and this pole, then we will get the radius vector of the point capital R. And what is the radius vector? The radius vector has been taken as equal to small r. This is the radius vector. And what would be the vectorial angle? This angle. This angle. This angle would be the vectorial angle theta of the point capital R. Got it? Now, you see, what we observe is that as because this is a perpendicular line, so this angle is equal to 90 degree, or this angle is also is equal to 90 degree. Therefore, if you consider this triangle, the triangle ONR, if you consider this triangle ONR with respect to this angle marked by this arrow symbol, with respect to this angle PON, with respect to this angle PON, this much length would be the base, this much length would be the perpendicular, and this much length would be the hypotenuse. Got it? And so, if we consider the cos of this angle, cosine of this angle RON, cosine of this angle, cos of RON, cos of RON, RON, cos of RON, that cosine angle should be is equal to base by hypotenuse. That means that should be is equal to base means this distance P. This distance P. Okay. And hypotenuse means this distance R. Alright. Then what would be P? You see, P should be is equal to R into cos of this angle. What is this angle? You see, this angle is equal to theta minus alpha. This total angle was equal to theta, and from this total angle we are subtracting this angle alpha. So we shall have theta minus alpha. So that is the relationship in between r and theta. This is the relationship in between r and theta. So that should be the equation of this kind of straight line. Got it? That should be the equation of this kind of straight line Rn. That should be the equation of this kind of straight line Rn. And over here the total reaction has been written in this way. So we will get P by R is equal to cos of theta minus alpha. That means so that P is equal to R cos theta minus alpha. So in this way we get the equation of a straight line. And if you expand this equation, cos of theta minus alpha, if you expand this equation, you see what will you get? You will get this kind of expansion. You will get cos of theta minus cos of alpha plus sine of theta sine of alpha, that is equal to P by R. So over here you see, if you divide this total expression by this constant quantity P, you will get this type of result, that 1 by r is equal to cos alpha divided by p plus sin alpha divided by p. So cos alpha divided by p into cos theta plus sin alpha divided by p into sin theta. So ultimately this equation can also be written in this way, that 1 by r is equal to a cos theta plus b sin theta. So over here these two quantities, capital A and capital B, these are two arbitrary constant quantities. You see, in case of Cartesian coordinates, we had the simplest form of a straight line is equal to y is equal to mx plus c. The equation of the straight line in simplest form was equal to, is the equation y is equal to mx plus c, where m and c, these are two arbitrary constants. So in Cartesian equations we had two arbitrary constants, and in polar equations as well we have two arbitrary constants, a and b. So in order to represent a straight line, whether in Cartesian form or in polar form, you always need to introduce two different constants. Over here, in case of Cartesian form, m and c are two different constants, and in case of polar equations, capital A and capital B, these are two arbitrary constants. Even if you consider this equation as well, hmm, you see, this p and this alpha, these are two arbitrary unknown quantities or arbitrary constant quantities. You have to determine these constant quantities in order to properly compute the equation of the straight line. So a straight line will always involve two arbitrary constants, whether they are represented in terms of polar coordinates or Cartesian coordinates, it doesn't matter. A straight line, try to remember this fact, that a straight line in two dimension will always have two unknown constants, and in order to compute two unknown constants you need two different conditions, so that you are able to find out the value of two unknown constants. Okay, so you remember this result, that in order to find out the equation of a straight line we always need you always need two different conditions, so that we can find out the values of these two unknown constants. These unknown constants may be in the form of alpha and this point small p, that may be in the form of m and this constant c, or in the form of a and this constant b. Whatever be the form, you always need two different constants in order to find out the equation of of a straight line. So a straight line, equation of a straight line may be written in this form: r cos theta minus alpha is equal to small p, or it can also be written in this form: 1 by r is equal to a cos theta plus b sin theta. So that is all about the straight lines. I am going to introduce the idea of circle, the polar equation of the circle. That would be the last discussion for this lecture. Hmm. We want to find out the polar equation of a circle. So we shall consider the same technique that we considered in case of straight line. So on a circle, we will have to consider an arbitrary point, and we need to construct a relation in between the polar coordinates of that point. Now, how to find out this kind of equation? You see, suppose this is the circle, and this O, this is the polar pole of that polar coordinate, and this OX is the initial line. Suppose this point, this is the center of the circle, and this center has this kind of polar coordinates r, comma, alpha. So this much distance, starting from O to this point C, this much distance must be is equal to the radius small, not r, yeah, rather not r, rather we consider capital R. You see, small r is to be reserved in for polar coordinates, capital R comma alpha, suppose. Hmm. They have taken capital R, yes, capital R, they have taken capital R. So suppose the center of the radius and the center has the vectorial vectorial angle alpha and the radius vector capital R. Hmm. So this much distance OC, this much distance OC, that distance should be is equal to the distance capital R, and this is the angle alpha, the vectorial angle of the point C. Okay. The radius of the circle is taken as equal to small a. Hmm. And suppose P, this point P is any arbitrary point on this kind of circle. Hmm. Then what would be the polar coordinates of the point P? Suppose the polar coordinates are r, comma theta. Any arbitrary point would have polar coordinates r, comma theta. Now, how to find out the relation in between this r and theta? You see, you can join this point P and this point C. You can join these two points. In that case, you see this distance PC, this distance PC should be is equal to the radius of the circle. And what is the radius of the circle? Radius is equal to small a. Okay. Therefore, you can consider the triangle OPC. This distance is equal to small r. This distance OC, this distance OC, this distance is equal to capital R. This distance is equal to capital R. And what is the angle? This angle. This angle. What is this angle? This angle should be is equal to theta minus alpha. Got it? And therefore, we can again apply the formula of a triangle that C square is equal to A square plus B square minus twice AB, and then cos of capital C. We can again apply this formula. Then through this formula, you see that C square over here, this distance is equal to, this can be considered to be is equal to small c. This can be considered, this side can be considered to be is equal to b, and this side, that is this much length r, can be considered to be is equal to small a. Got it? Therefore, you see over here c square. C square means c can be considered to be is equal to small a over here. As I told you, c square is equivalent to this radius small a. So in place of c square, we can write a square. Okay. And in place of a square, we can write this distance r square. So this r is actually nothing but is equal to a in this formula. So in place of a square, we can write r square over here. And in place of b square, we can write this small r square. So this b square can be written as small r square. So what would be the formula? A square is equal to r square plus small r square minus twice small r capital R, cos of this angle, their angle in between these two, and that is actually the angle theta minus alpha. So cos of theta minus alpha would ultimately appear as this angle. And therefore, if all these quantities a square, r square, capital R square, etc., all these quantities are kept in a single side, then this equation can be written as this kind of expression: r square minus twice r small r cos of theta minus alpha plus r square minus a square is equal to 0. So this would be the equation of this kind of circle. That is actually the relation in between the polar coordinate r and this angle theta. That's why this gives us the equation of the circle. So in this way, we find the equation of the circle. Now there are some special cases of this circle. Suppose this point O lies on this circle over here. Suppose if this is the position of the point O, then you see then this much distance, this distance would become is equal to this distance, that is actually the radius. Hmm? And that is, therefore we can say in that case r would be is equal to the radius small a. So if by chance this point o lies on the circle, in that case r would be is equal to a. So if you put r is equal to a in this relation, you will ultimately get this kind of formula. In everything, this r is equal to a in this relation, you will ultimately be will have this kind of formula. Just by putting r is equal to a, we will get the result that small r is equal to twice a cos of theta minus alpha. So this is the special case. That is when the circle passes through the pole, or pole lies on the circle. Got it? So you have to remember this formula as well as this formula. These two, this is the general formula of a circle, and this is the special case. This is the special case when the circle passes through the pole. Here, so try to remember these two formula of a circle. That's all for me today. Thank you for being with me in this class.